All right. Well, this is the first time I've given a talk by Zoom, so I'm used to kind of looking at the audience and saying hello to everybody, and hoping everybody's doing well. So consider yourself looked at and wished well. So today I'll be talking a little bit about how you know. The continuum version of acceleration can be brought into the PDE framework. And there was a nice talk that was already given a couple of days ago by Michael Jordan, in which he talked about, kind of the continuum version of acceleration. And there's some interesting dimensions to it when you go into the framework of PDEs. Some new things come out that are interesting things to pursue. So I'll be building very, very largely on top of that kind of seminal work back in the 2016 paper with Bisono and Wilson and Jordan. But you'll see some things that come out in the framework of PDEs that I think are kind of interesting. So I'm gonna there's kind of four works that we've kind of put together on this, and the logical order is a little bit the opposite of the historical order. But I kind of follow the logical order, and we'll talk a little bit about doing PDE-based optimization on flat spaces. We'll look at problems like denoising, inpainting, deblurring. You can also use this for the obstacle problem, and then we'll look on more general infinite dimensional manifolds, in particular the manifolds of curves, active contours, active surfaces. I won't be demoing today, partly for time, but also because my colleague Ganesh Surendamurthy is really the one that drives this last piece of the work on diffeomorphisms. But you can also use this in the context of non-rigid image registration for optimization over the space of diffeomorphisms. So let me just quickly go through the problem we were working on several years ago that kind of caused us to stumble onto this, and it has nothing to do with PDEs, at least not on the surface. But we were looking at doing myocardial segmentation in 3D. With trained 3D shapes. So what you see in this example here is the initialization of an automatic segmentation algorithm, and you can see that there's the humans can kind of do a fairly good job of seeing where the left ventricle is. These are contrast enhanced CT images. So in this case, the contrast agent is in the left ventricle; it has not reached the right ventricle yet. So you can see it's a much harder segmentation problem to find the boundary of the endocardial boundary of the right ventricle, as well as the epicardial boundary here. So we have a set of expert hand-segmented volumes that we did some training on. We came up with some shape priors for these three different volumes. You're seeing curves here because they're just cross-sections of a 3D surface. And then we blend these together in one big non-convex optimization model, in which we have a fitting cost where we those three surfaces, as long as they don't overlap each other, will divide your volume domain into four regions. So we have the region for the left ventricle, the right ventricle, the myocardial muscle, and then the background. And then we just fit some constants to the endocardia and the myocardium. In the background, we have kind of a two-level C-means blend of modeling the background for bone as well as for fluid. And then that already makes the problem non-convex here. And then what really makes it non-convex is we impose these inequality constraints that we know that the intensity of the left ventricle should be the largest. So that means should be or the bone should be the highest. So that should be the highest, then the left ventricle intensity, then the right ventricle, then the myocardium, and then the fluid. So we impose those constraints. And then another thing that makes it non-convex is we impose a penalty on the overlap between the regions. Ideally, we don't like these things to be, they should be separated actually, but at the very worst, they shouldn't overlap each other. So this is the optimization. It's a finite dimensional optimization problem because there's a finite set of parameters for the pose of each of the three surfaces, plus a finite set of parameters for the shapes since we trained on them. And this is the optimization result that we get. And here's a 3D visualization. So this is the result that we got on one of the 3D volumes that we left out of the training set. And we compared, that's what you see on the right. And then on the left, you see the manually traced results assembled together into a volume by a trained radiologist. So we spend a tremendous amount of time putting together the system with the constraints and the model and everything else like that. And for a long time, we were having a terrible problem with not so much with local minimizers, but with very narrow descent values when we're using gradient descent for this. And so what was happening is that the overlap penalty that we would put in place, as long as the three regions didn't overlap, that penalty wouldn't apply. And so you go down your energy, functional nice and smoothly. And as soon as overlap occurred, since it's such a strong overlap penalty, suddenly there was a force that was applied in the gradient. And that would change very abruptly the direction of the gradient descent. But then as soon as you got kicked out of the overlap, then the whatever force was bringing you towards the overlap kicked in again, and you would bounce back and forth through this really, really narrow valley in the energy landscape. And so I can kind of show you that effect here. So here's a part midway in the middle of the gradient descent process. So you can see three, cross sections in three different directions here. And if you watch, you see that you see this jitter. You can see the curves kind of going in and out, pulsing almost like a heart. And that's exactly what's happening. We're stuck in this narrative, and we are very, very slowly making progress, but it takes forever. I mean, we have to do tens of thousands, I mean, maybe even hundreds of thousands of iterations. And in just a second, you'll see a plot. I fixed it at 20 iterations here. So here you can see a plot of the energy, and you can see that here it doesn't look like we're making any progress. But if I did about 10,000 iterations, you'd see slow progress being made. So a really easy fix to this was just to add momentum to this. It's a classical way of solving the problem. And so you just, you compute your new gradient, and you go in kind of a blended combination of your prior search direction and the gradient search direction. So this is some parameter between 0 and 1. And so this shows the difference and the importance of the momentum or the acceleration. So the red curve shows you the gradient descent. And here you can kind of see that progress is being made painfully slowly, whereas the momentum term sails us through that quite nicely. So I got interested in this in general for more flexible active contours, and at the time, in which case it was no longer a finite dimensional optimization problem. There wasn't any trained shape prior anymore. Of course, this finite dimensional approach goes back to Nesterov, actually even before, with heavy ball methods. And in 2016, Stefano Salato pointed out to me a really beautiful paper by Webizona, Wilson, and Jordan, in which they actually describe a variational framework, show how you can put all these various momentum-based techniques, including Nesterov, including heavy ball, in a variational framework in terms of the Bregman divergence, and a kind of generalized Lagrangian made from the Bregman divergence, which they call the Bregman Lagrangian, right down here. And so in this case, the idea is that you have the energy that you're trying to optimize, which they're calling U, and that behaves as a potential energy term. And then you have this other term that depends on basically the dynamics of the optimization. It's so if you take a special case, if you just look at the Euclidean distance, you get a simple version, which looks like a kind of a generalized version of the classical action, in which you have a velocity and a position. And then you have a potential energy term, but then you have these time-dependent multipliers, which, of course, that means that you don't necessarily conserve the resulting Hamiltonian anymore, and you can have a slow dissipation of energy. So instead of descending directly on the original cost function, which is U, you descend on the Hamiltonian. in this more generalized framework. So they show that you can get Nesterov and its various versions as by special choices of these parameters. And this was already mentioned in some previous talks. So I don't want to get into the details of that. But I just wanted to give tilt my hat to this, because this was really what launched the body of work that I'm about to show to you now. So we don't use the Bregman divergence framework. We stick with the simple Euclidean case because we want to do this on a manifold, and so we want to work we want to be able to find this in the tangent space of the manifold. We need to come up with a notion of kinetic energy that's based on velocity and not finite steps, because as soon as you're on a non-flat curve manifold, which is what we're going to be in the case of curves, you have to follow geodesics, and so we want to get away from that. So we take, in one sense, a more specific, slightly less general version of it, in the sense that we're going to go back to the Euclidean case, but then we're going to lift it up into higher dimensional manifolds. So in that sense, it's going to be generalized a bit. But the key point is that, because of these time-dependent forces, this is, the optimization time, evolution time, the resulting Euler-Lagrange equation of this action integral gives rise to frictional forces you can control, and this gives you the damping, and that's what allows you to converge at the end of the day. So the motivation, the interpretation is quite intuitive, kind of from physics. That if you think of a ball that you drop on a really undulating terrain, that typically it doesn't get stuck in the first local minimum, just because it has some momentum that's accumulated by the time it gets down. And so when it hits a minimum initially, it overshoots it. But because of frictional forces, the overshoot, it doesn't just continue indefinitely until it reaches its original height. It eventually loses energy and will oscillate into a nice deep minimum for you. And it's exactly that overshoot that is your friend, because that carries you past these less desirable local minimizers and gets you into a deeper well with a wider attraction basis that can actually support that overshoot and then allow you to come back. So that's the quick intuition. So now we can generalize this to the PDE framework, and we can consider the kind of a classic calculus of variations problem, where you have a term that depends on a function u, and then and perhaps a regularizer that depends on its gradient. And so we're going to look at this kind of general class of optimization problems in the infinite dimensional space. We'll just look at L2 for the moment. So if you write down the Euler-Lagrange of this type of cost functional, you can write the gradient. You can effectively say gradient equals 0, and that gives you the following Euler-Lagrange equation. And so and then you can form a gradient descent out of this by now introducing a time derivative, and then and setting the time derivative of u equal to minus its gradient. And so that gives you the classic gradient descent. So now what we do is we take that same cost functional, that becomes our potential energy term, and then we take the time derivative of the evolving estimate of the function, and then we multiply it by some kind of a density. So when we're in finite dimensions, we can just think of evolving a single point, in the continuous. We're just evolving a point in some high dimensional space. We can think of it as a particle with unit mass. And in the infinite dimensional case, we could think of it that way. We could think of it as the infinite dimensional particle with unit mass, or we could more generally think of mass distributed along the domain of the function. And so we give it a density now. So there's a mass density that multiplies the local time derivative, and then we integrate that over the function domain. So that becomes our general notion of kinetic energy here. So now if we compute the Euler-Lagrange of this kind of action integral, we get a second order PDE of the following form. So here's the gradients that we would normally have in gradient descent. So this will involve all the spatial derivatives depending on the regularizer and what else, whatever else appears. Here's your density term, which again doesn't have to be constant. It can be distributed. It can even be time dependent. In this case, we've shown it space, but it could also be time dependent if you like. And then here's the frictional term that arises, and then here's just another adjustable parameter that you used for the potential energy term. So as you let the friction go to infinity, you get the gradient descent as your infinite friction limit. This was already pointed out in the 2016 paper. It's kind of well understood by those that are doing this in the finite dimensional case. So now let me say a little bit about numerical schemes for solving this class of PDEs. So focusing just on the time derivative for now, and because obviously space derivatives are going to be involved in the gradients of this function. That's kind of the difference with the PDE framework versus the OD framework, is that we're going to have a bunch of space derivatives in here. But focusing on the time derivative here, if we just do a simple forward Euler discretization of the continuous gradient, then we get the following kind of discrete evolution. That the increment of u at each point x is going to be our time step times our estimate of the gradient. So we have to discretize this somehow as well. And now, if we do a Fourier analysis, if we do kind of von Neumann analysis. Now, of course, that assumes that we can linearize this. So assuming you can linearize this, if it's not already linear, then you can apply von Neumann analysis to this update scheme. And what you'll get is that you'll get in this explicit update step, that in frequency, the frequency constant at any given frequency gets decoupled from all the other frequencies, and there's this amplifier that occurs right here. And in general, you can stably discretize this. As long as this thing doesn't have, you can choose delta t such that this thing doesn't have a complex amplitude greater than 1 anywhere. So this is the basic, way of computing the CFL condition. So now, in this case, what shows up in front of the time step is something, and again, this will depend on the nature of your gradient, but you'll get some complex function here, which I'm calling the gradient amplifier, because that's the part that multiplies the linearized version of your gradient after you do the Fourier transform. And so the stability condition for the numeric implementation is that your time step has to be less than or equal to the gradient amplifier here plus its complex conjugate divided by its complex amplitude squared, or otherwise twice the real part of 1 over the gradient amplifier. Okay, so now it's quite common in several regularized optimization problems for this gradient amplifier to be purely real, especially in a lot of elliptic problems that we're going to be looking at. And in that case, the CFL condition that I wrote more generically there has the following form: that you just have to you choose your time step be less than 2 over the maximum value of your gradient amplitude. The maximum is computed over all frequency. Okay, so that's for gradient descent. Okay, that's it. Now, what about for PD acceleration? So for PD acceleration, if we do a simple, in this case, we have to discretize a second and a first derivative in time. So if we just use central differences for both of those, and again, we use whatever linearization we have of the gradient that we considered before, then we get this following update here. And in that case, the CFL condition, in the case that the gradient amplifier is real, looks like this. So you notice that we've gained in a significant way that now it's 2 over the square root of the maximum value of the gradient amplifier. So that's extremely significant in the elliptic problems that we're going to be looking at that are highly regularized. It gives you a huge benefit in terms of being able to numerically implement this much faster than you would with gradient descent. Plus, of course, all the other benefits that come with acceleration, but you get this numerical benefit as well. So let's take a look at a class of regularized inversion problems that would benefit from this significant boost that you can take discretely in time. when you do acceleration. So we consider a class of reconstruction problems where you have some measurement G that is perhaps corrupted by noise. It might be blurred, and you want to compare your reconstruction passed through some kernel, and then you have some fidelity that measures the norm of that difference. And you have a regularizer that depends on the norm of the gradients. Okay, so these are the two things. So the constraints are that this is monotonically increasing, so its derivative is positive, and this should also be monotonically increasing, as well as be convex. Its second derivative should be greater than 0. So those are the conditions. So now if we compute the continuum gradient of this, we get kind of the following set of terms. And if we plug that into the accelerated PDE framework, we get this nonlinear wave equation. So gradient descent would give you a parabolic kind of reaction diffusion type of equation, whereas here that transforms into a nonlinear wave equation. So that's which has completely different characteristics, of course. And so a nice thing is that in the linear case, and for this, if there's questions, I'm going to refer to my collaborator, Jeff Calder, who's the one that worked this out very nicely. You can actually compute an optimal damping. And it turns out that a constant damping is the way to go. And once you depending on the nature of your regularized, you get an elliptic operator in the resulting PDE. And the optimal choice of the damping coefficient here, if you use the constant damping, is just twice the square root of whatever your fidelity penalty was here, as well as the first eigenvalue of L. That's in the Dirichlet problem. In the case of the norm involvement, it would be the first eigenvalue that corresponds to a non-zero eigenfunction. And so this gives you an optimal convergence rate below here. So this is a really nice thing that shows up in the PDE framework. Now, so we can look at the easiest scenario, which is quadratic regularization. We'll just assume an identity for a kernel for now. So we have a function like this that we're trying to optimize. And in this case, we get a linear wave equation as the resulting accelerated PDE. So let me show you a demo of how this works. I chose this one because it's the most interesting to watch. Obviously, quadratic regularization is not very useful in an image process, it's very blurry, but it demonstrates very nicely the qualitative difference between the resulting gradient descent process, which manifests itself as a parabolic diffusion type equation, versus the accelerated descent problem, which manifests itself as a wave equation. So here is an example of doing a running gradient descent, and as you would expect, this has a kind of a local diffusion effect, and there's a global property in the sense that the diffusion, little by little, propagates from pixel to pixel to pixel, but that global effect is obtained very slowly over time, which is part of the reason you need to take a very small time step. That's kind of the intuitive explanation of the CFL condition. Now, if I reset this and I don't change any parameter, I'm just going to turn on acceleration now. And now I rerun it, and let me choose. I'm not going to choose the optimal damping. I'm going to choose a really small damping, just so that you get the visual effect of what this is doing. And then I'll show the optimal damping in just a second. But when I run it now, you see a very different behavior. You see waves propagating, and this is carrying information across the domain of the image much faster than what you would get in diffusion. Now, of course, right now the damping is ridiculously small, so it's taking a very, very long time to converge, but you do see at least the intuitively and qualitatively effect of how the acceleration propagates information very quickly across the entire data set, which is part of the reason that it's more resistant to local minimizers. Now, if I use the optimal damping, the way that I do it in this interface is that if I put in 0 for the friction, then as soon as I hit evolve it, it will automatically use the formula to calculate the optimal damping. And there's the result. So there's the converged result. That took about 130 steps, whereas the gradient descent takes about 10,000 to get to about the same energy here. So you get fewer steps, and part of that is just because of the fact that you're restricted to a much smaller time step in gradient descent. Okay, so that's a quick demo, kind of showing the difference in the transformation of the PDE plus the effect of the more generous von Neumann CFL condition when you look at the wave equation compared to a diffusion equation. So now we can look at Beltrami regularization, which is one step closer to TV. And in this case, so we're changing the regularizer to the Beltrami one rather than the quadratic penalty. And now we get the following nonlinear PDE, but it still has a nice quasi-linear form. And we can still give an estimate of the optimal damping by considering this denominator here at its worst case scenario, in which case the gradient of the image is 0. And then in that case, its local linearization looks like the quadratic one. So you could, if you plug that into the formula, you get the following estimate for the optimal damping. Now, as you let your Beltrami parameter here go to infinity, this converges to total variation. Now, you can't do an optimal damping anymore for this, but you still get damping, and you still get an improved, convergence. It's just that you have to kind of manually, come up with a reasonable damping for this one. There's not a nice quick formula for it. But nevertheless, you do get the following PDE. And so here's this application for image denoising, and we compare it with split Bregman as well as with primal dual. So here's a cross section of that result, and the green is showing. The blue is showing the PDE acceleration approach. The red is primal dual, and the split Bregman. So this is at 4 different times during the evolution. So you see early on the behavior of the algorithms is very, very different, because in PDE acceleration you still have a tremendous amount of high frequency information. This is that wave action that's basically carrying that local information globally across the image. As that occurs, these oscillations start to die down due to the damping, and we converge to results that are just as good as just to say with a much simpler kind of local explicit implementation. We even get, in some cases, slightly better if you look at the results at subsequent iterations. This is PDE acceleration. So you see the green is in the beginning, then the red is midway through, the orange is further away, and then finally this is the converged result. And we get an even better edge preservation here than we get with primal dual. So now let me shift gears, and I haven't shown examples here for the obstacle problem, but that's another application of doing this on flat spaces. So let me shift gears now and talk about what do you do when you're on more complicated infinite dimensional manifolds? In this case, the manifold of curves. So this brings me back to my original interest, which was in active contours and ultimately in active surfaces. And in particular, I'm going to be talking about level set implementations of active contours. And the reason that interests me the most is that when you go to 3D, it's very convenient not to have to deal with triangulated surfaces. So these methods were introduced by Ocean Sethian several years back in the 80s, and in this case, you evolve the function by evolving a graph. But we formulated the problem first as a curve evolution, and then once we have that, once we know our curve evolution, we can construct the corresponding level set PDE. So this is kind of the original sense in which level sets were used for curve evolution. Later, there was a rich body of work that was begun by Chan and Veze, in which you actually build the level set representation into the energy itself, and then you write down a level set evolution directly from the order Lagrange. So in this case, I'm retreating to an earlier approach, which is where you first write down a PDE for the evolving curve that's geometric, and then you write the level set equivalent of that. And of course, this gives you the advantage of topological split and merging during the evolution. So what do you do here? So here's another area that some interesting things occur in the PDE framework that you don't have to worry about in the finite dimensional case. And so this again brings us to mass. Where's the mass? So the simplest one is that you think of mass as a density that's uniformly distributed according to arc length. This is the simplest one. It's not intuitively desirable in the sense that as the length of the curve changes, if you use a constant density, you're not conserving mass, which from an optimization standpoint really doesn't matter. If your goal is just to converge to some energy, fine. If you were trying to model physical mass, then and you had conservation, then of course you would need an additional constraint, which we'll talk about in just a minute. But we'll start off with a simple one. So this now becomes your kinetic energy term. So here's your curve evolution. You integrate this over the contour. This is integrated with respect to arc length. That's what makes this nonlinear. That's what makes this space kind of curved and nonlinear. And then in the case of a constant density, you can pull it outside, and then you can treat this as kind of as an infinite dimensional velocity of the velocity squared of an infinite dimensional particle is kind of the one way. If you pull the density inside, it's a more general type of interpretation. So again, you compute the Euler-Lagrange equation of the generalized action that we had before, but now in this contour framework, and you get a more complicated type of wave equation that that includes advection, reaction, friction in a more complicated sense. You can see that it's a wave equation because you get the second derivative in time here. And then if you look in this term, in this more complicated term, you see there's a space derivative of the curve here and there's a space derivative outside. So it's more complicated because there's kind of a parallel transport that's occurring that's kind of blended into all of this stuff as you move it across the manifold, which is again why we abandoned the Bregman version of the Lagrangian and stuck with generalizations of the Euclidean one that we could work in the tangent space. But that's an additional problem that we don't have to deal with if we don't look at finite jumps. So now, how do you implement this in a convenient way, especially with level sets? So to do this now without directly parameterizing your curve, you can take this and if you can use the kind of normal and tangential evolution of the curves. So if all I care about is the geometric evolution of the curve, then I really just care about the normal evolution. Now, when I'm doing gradient descent, I'm basically just setting this time derivative of the curve to the gradient, and I can just ignore the tangential term. It's no big deal. So I can take the normal component of the gradient, and that's what I set it to. Once I'm in the second order framework, it's not so trivial to just abandon this tangential term because so if you take the second derivative of this, then you can look at what the evolution of the tangential and the normal speeds are. So now here's a really nice thing. If this is the evolution of the tangential speed, and if you notice, as long as you start off with 0 tangential speed, it stays 0. So that's now, if you don't start off with 0 tangential speed, then you have to model this. So the beautiful thing is that as long as I can still essentially ignore the tangential component of the evolution, as long as I start off with 0. So this is a really nice thing. It's kind of described more in detail in the paper. So now I can just look at what's the evolution of the normal speed. And in general, it's coupled to the evolution of in general, both of these, as you can see, they're coupled to each other. In general, it's coupled to the tangential speed, but if I take the special case where I set the tangential speed to 0, then I get the following kind of reaction equation for the evolution of the normal speed. And as you can see, it depends on the curvature of the curve. So now if I know how the normal speed is evolving, I can just split this into a simultaneous evolution of the curve according to its normal speed, and an evolution of the normal speed itself. And if you're using level set methods, you can do this in the narrowband framework very efficiently. So you evolve the just around the zero level set for the curve, and you also within that narrow band are evolving and transporting an evolution of the normal speed function as well. So you have this coupled evolution of two PDEs. And so that's what that looks like here. And then, so now if you write down the implicit level set representation of this, you have to define this normal speed in a neighborhood around the curve. We'll call that the extension B hat. And then psi will be the level set function itself. And so that you get this coupled evolution of the level set function as well as the extension of it in the neighborhood of the zero level set. So these are the two things that you evolve in parallel with each other. All right, so can you be more sophisticated about this? So again, in the PDE framework, we have this whole distributed mass, which is a whole new thing that we can play with. And as I said, you could just take the simplest case where the mass is represented by a constant density. In this case, on the case of an evolving curve, it's the density with respect to arc length. Or you could allow the mass to evolve as well. So the mass can change spatially and temporally. And you can even impose, if you want, a conservation of mass. So the really nice thing about this variational framework that we're borrowing from the 2016 paper of Webisono, Wilson, and Jordan is that because we have this variational framework, we can throw in Lagrange multipliers very nicely. We can have constraints. And so one of the things with traditional momentum is if you construct gradient descent and you have a Lagrange multiplier and you have a constraint and you can project to make sure that you stay within the space of your constraints in the gradient descent, that's easy to do. Once you throw in momentum, that's all off. But if you have the variational framework, you can reformulate the Euler-Lagrange of the action integral and put in the same Lagrange multiplier. It's not as simple as an orthogonal projection as it is in the gradient descent, but you can still do it. And so in this case, we can put in this local mass conservation term. So this is basically a continuity equation that assumes that mass is conserved not just globally, but locally as well. And we throw this in as a Lagrange multiplier into the generalized action. We recompute the new Euler-Lagrange, and we get a system of three evolving PDEs. So one is the evolution of the velocity of the curve. Here I've done it in vector form, as opposed to just the normal scalar speed. This is the evolution of the curve itself. If I know the velocity, this is the normal evolution of the curve. I look at the normal component only. And then this is the evolution of the mass. Now, the reason that I'm going to the vector form for the evolution of the velocity is even though I'm ignoring the tangential component for the evolution of the curve itself here, I still need tangential and normal components of V in order to evolve the mass. And now, this is a more complicated coupling of three different evolving systems. So that simple thing that if the tangential velocity is zero, it stays zero, that doesn't apply anymore. So I use that for the evolution of the mass, but I ignore it for the evolution of the curve because I just geometrically care how its geometry evolves. But it's still modeled in these two equations here. And so now you can start to see a connection between this and optimal mass transport as well. And when we go to, although I won't be showing it in this talk, when we go to this framework of diffeomorphisms, and we're trying to optimize, over the space of diffeomorphisms, in this case, the mass is distributed spatially. And now it really does look like optimal mass transport. I mean, you really get back a lot of similar looking PDEs that you see, especially in the fluid dynamical framework of optimal mass transport of Benamou and Brenier. Anyways, a nice thing that you can do as well, and there's a heuristic way and a more principled way, is several years ago, in order to try to make active contours a little bit more robust, instead of writing the gradient descent with respect to the classical kind of geometric version of the L2 norm, we looked at the gradient descent with respect to a Sobolev norm. And we called these Sobolev active contours. And in the case of the Sobolev active contour, you can get the Sobolev gradient evolution of the curve from the L2 gradient of it. It's not really truly L2, but it's like the geometric equivalent of it. By convolution. You basically have to solve a linear operator. Now, in the 2D case, in the case of a curve, there's a trick. There's a very specific type of Sobolev inner product that you can use in which you can do the convolution as a one-time double integration. So the cost of it is not much worse than just a traditional active contour. And it essentially gives you a spatial averaging of the gradient, because at a given point on the contour, the Sobolev gradient force is kind of an average of the non-Sobolev gradient forces that you would get as you visit other nearby points on the contour. It's kind of a weighted average. So it's kind of a spatial way of integrating gradient information. Whereas you can think of acceleration as a temporal way of integrating gradient information, which is, of course, more efficient to do computationally. But we can get some spatial regularity, too, in the gradient calculation by simply adding a diffusion term to the evolution of the velocity. So this is the evolution of the velocity, this first few points that we get from the strict Euler-Lagrange of the generalized action. If we just add a diffusion term to it, this will give in addition to the temporal averaging of gradient information that occurs due to the acceleration process going on, it also gives us a spatial averaging as well. And it gives you kind of an extra degree of regularity. So this is, again, another kind of cool thing that shows up in the infinite dimensional PDE framework that you don't see in the finite dimensional case. Now, we can be more principled about how we do that spatial averaging. Again, going back to kind of continuum mechanics as the motivation for it, if you imagine the mass on the contour as being a fluid that has a certain height. So now the fluid, instead of is kind of sitting on a thin bucket on top of each point of the contour, and its height can change, and so we can attribute a potential energy to the mass distribution as well. In addition to the kinetic energy, you can have a potential energy distribution for the mass itself that's independent of the cost function they're trying to optimize, which doesn't depend on the mass, right? The mass is just there to help the dynamics. So if we consider like the analog of a gravitational constant, and we take this mass distributed along the curve with respect to arc length, then we can describe this as the potential energy of a given mass distribution. And if we penalize, if we choose the gravitational constant large, then we prefer a constant density. So we're not imposing a constant density, but we prefer a constant density. So what happens now, and the reason you can get Sobolev-like effects, it's not Sobolev, okay, but it gives you similar effects without having to invert a linear operator every single time step, because what will happen is, suppose you start off with constant density on the curve. Now you evolve a little bit, and let's say that a little piece of the curve starts to, shoot away from the rest of the curve, which introduces a huge, a large derivative in the velocity itself, right? Something that Sobolev would discourage. Well, what will happen is that since you have local mass conservation, you've locally increased arc length in a tiny piece of the curve. That will cause the mass to shoot down. It'll induce a big change in the density, and this will jump up since it's conserved mass, and since you've deviated very sharply from a minimum energy state of constant density for the mass. Now your potential energy of the mass distribution shoots up, and in subsequent iterations, it tries to correct that. And one way it tries to correct that is to cause nearby points around the curve to follow the evolution of the points that tried to shoot away, in order to try to bring the mass distribution back down to something that's more uniform. That, again, that's not Sobolev, but that gives you a similar qualitative effect without the pain of computing Sobolev. finally, the last thing that's easy to add is that you can add, since the velocity, since so we have acceleration here. So if we add noise to the acceleration, which seems like, why would you do that? But it's just a stochastic term, so it's another way of getting out of local minimizing. Since it gets integrated twice, you still get a continuous and differentiable curve evolving over time, which means since it's differentiable, you still have a well-defined unit normal. So all of those equations that are wrote down, we can still handle, even if you throw in a stochastic element in the midst of well. So this would be like a stochastic term that you could add. In practice, we haven't needed it, but it's cool that you could do this because you would not be able to do this in gradient descent, because although you'd still get one level integration that gives you continuity, you would immediately lose a well-defined unit normal if you tried to do this in gradient descent for curves. So let's just play. Let me just in the last 4 minutes here show you the effect of this. So here's the behavior of continuous gradient descent for an active contour versus the accelerated gradient descent using this kind of nonlinear wave PDE. So in the case of gradient descent, of course, this is an easy image to segment. This is for illustrative purposes only, of course. You see that basically each part of the contour evolves locally. The parts that are in the bright areas move in, the parts that are in the dark areas move out. This is a simple Chen-Vézé style energy functional. It's quite easy. You see this exactly the behavior that you'd expect for a simple region-based active contour. Okay, so if I start off with the same contour, I don't change any parameters, but I turn on acceleration, you'll see the wave effect of this in the nonlinear form showing up in the evolution of the contour as well. And you see that it takes on a much different path and different behavior. And this is kind of fun to play with. If you start with something outside like this, you can really see the wave action doing interesting things here. And now, a question is, why would you want this? I mean, wasn't the previous behavior of gradient descent much better? And well, yeah, in this noiseless, simple, easy to segment image with no local minimizers, yeah, it was better. And this just seems like an intellectual exercise for fun that we're doing here. But as soon as I add noise, this makes a huge difference. So let me also consider a case where we require a topology change so that you can see the benefit of using this in the level set framework. So here's an example of starting off with two shapes, and I've added a lot of noise. I'm using the same active contour model. Now, when I run gradient descent, almost immediately I get stuck in noise. And it doesn't matter where I start. I mean, there's tens of thousands of local minimizers. Almost anything you start with will get stuck very quickly on the noise. Now, you could add a regularizer to your energy functional. Of course, that's going to sacrifice capturing the sharp corners of the square. That's not the point I want to illustrate. Without having to do that at all, using exactly the same energy and the same level of regularizer, if I simply switch this to the accelerated descent, then you see that the behavior is much more regular, first of all. I don't get stuck in the local minimum. You see that isolating effect. What's really compelling is this. Let me turn back on gradient descent. Let me let it get stuck again. Okay, so now it's stuck. It seems to be at steady state now, so I'll stop it. So I got stuck in local minimum. If from the local minimum, I switch to the accelerated model, so numerically, you're never exacting the local minimum, right? You isolate sub-pixel around it, right? That's enough to pull you out in many cases when you use acceleration. So starting from this local minimum, without changing any parameters, except that I just turned on acceleration, if I now evolve this, I get out of the local minimum and I get back a decent answer. So now let me show one last demo and then I'll switch it over for Q&A. But these were toy examples. There are much easier ways of segmenting those 2D images. Okay, so I'm not suggesting this is their approach. The more interesting thing is when you start to do a more complicated non-convex optimization problem with active contours, and especially active surfaces. So I mentioned that Sobolev active contours, there's a trick that you can do them rather inexpensively in 2D, but in 3D, the Sobolev gradient of an active surface is very painful. I mean, so you basically have to solve a Laplace Beltrami type operator on the surface every single evolution step, then take a step, and then it's a very, very expensive. The trick that works in 2D does not work in 3D. But here, everything I just showed you, those coupled sets of PDEs, there's nothing special about 2D in any of them. They generalize just fine to 3D. The evolving mass, the evolving level set function, the evolving velocity, all of those generalize straightforward into any dimension that you want. So let me just, let's see, let me shut this and I'll end with this 3D demo. Let's see. Okay, so this is using active surfaces for 3D stereo reconstruction. So this follows up on joint work that I did several years ago with Stefano Solato, where we used active surfaces for stereo. Now, if you look at these images, you might be tempted to think, oh, wow, look, this is just simple, region-based active contours. There's convex versions to solve this. But it's deceiving because we're not evolving these regions. What we're evolving in reality is a 3D surface. And we project that 3D surface onto the images that you see here. So these are 4 out of 32 images. In fact, if you want, these are all the images. And so you can kind of see the projection of our initial sphere that we've put on these surfaces. Now, the cost function that we're using to invert this is of course, we use a standard perspective projection of the 3D surface to get these regions, and then the goal is a Chain-Vézi-like idea that I have a constant radiance on the surface, a constant radiance for the background, so that after projection, I get binary images that have that foreground radiance inside the projection and the background radiance outside the projection. Now, it's very easy to see and imagine that if you compute the gradient of that without any regularizers, that the only place that there's going to be gradient forces on this 3D surface are the back projected occluding boundaries of these silhouettes. So you have gradient information on a very thin set on the surface, and unless you somehow regularize that, you don't get a very good result. And so here I'm showing 0 regularizer. I'm not penalizing the surface area, and you can see if I start to evolve this. You can see that kind of the surface is becoming very irregular, and that's because the occluding boundaries are changing in a really complicated way. That's what makes this problem horribly, horribly non-convex. I mean, so it's and you can kind of see that if you look at these are the depth estimates. These are the depth images produced from our current estimate of the surface, and you can see that these are the occluding. The red points are 3D points of my grid projected down that are determined to be on an occluding boundary. And as you can see, even these occluding boundaries in the depth itself don't really count because we're only looking at the occluding boundaries of the silhouette. And that really changes in a very complicated way from view to view. So you can kind of see that going on here. So you really need to regularize this. And that regularization slows down your gradient descent really hard. So let me put back the images. I'll show you gradient descent with the regularizer, and then I'll show you the acceleration. And then I'll be done. Let me put this back here. Let me reset this. So now I'm going to put in a regularizer, so that as I pull little thin pieces of the surface, it brings things around neighborhood parts of the surface with it in order to try to keep the overall surface area low. And this is gradient descent. And so it eventually gets there. I have to do about 1,000 iterations to get there. All right, so let me reset this. Let me turn on acceleration. Let's see. Here we go. So I'm not changing any parameters. I'm just switching from no acceleration to acceleration. And so now when I evolve this, you can see, I'll show you, I'll redo it one more time, showing you every single update so you can see the wave action better. But you can see already after just 100 steps, I'm almost there. Here's 140, and I think this gets there in about 160, 170. There you go. And now, you might be wondering, what are all these little ripples on that? That's not lack of regularizer. Those are the waves that occur. And so to see that better, let me those will eventually dissipate away. So let me reset the surface. I'm going to show you, I was showing you every 20 steps. Let me show you every step, and you can see the wave action occurring. So I'm going to show you, it'll be slower to watch, but you'll be able to see it's kind of cool. If you watch the evolution now, you can see the waves in 3D. And in the beginning, they're very low frequency waves. As it starts to converge and find structure, you get waves at higher frequency and smaller amplitude, and that's what's happening. And you can see if I simply up the friction, those go away. So you can see that this is purely due to the wave action. So if I go from 16, say, to multiply by 4 to 64, and I start evolving, very quickly see those waves start to dissipate. So so that's it. So I'll stop there. And if there's any questions, I'm happy to ask. If anybody has questions especially on the optimal rate, I'll defer those to my colleague Jeff, who should be online with us right now.